In section 2.2, we'll be talking about differentiability. So in section 2.1, we defined what a tangent line was, and so it shared the slope with a curve and shared a point. And so when we talked about though, we did not cover the possibility of a vertical tangent line. And so remember that vertical lines have a slope that is undefined. And so we can't just say that the tangent line is undefined there. We want a more specific definition. So our definition of a vertical tangent line is that if f is continuous at x equals c, and the limit as h approaches 0 of f of c plus h minus f of c over h is infinity, or the limit as h approaches 0 of f of c plus h minus f of c over h is equal to negative infinity, then the vertical line passing through that point is a vertical tangent. You can see it in the graph over here. So essentially it's like the function is almost going vertical, although it can't be like a vertical line straight up and down because then it wouldn't be a function. So one of the functions that has a vertical tangent line is x to the 1/3. And so let's actually sketch out that graph and think about it. So if you remember x to the 1/3, so that's cube root of x, it looks like x cubed but on its side. And so you might be able to tell here that it has a vertical tangent line at 0. So part of my graph just disappeared. Not sure what happened there. But it looks like that. And I think if you actually look at it on your calculator, you can see it, the vertical tangent a little bit more. But let's actually prove it algebraically. So we're going to use the limit as x approaches c formula, so limit as x approaches 0 of f of x, which is x to the 1/3, minus f of 0, which would be 0, all over x minus 0. That gives me then just x to the 1/3 over x, which is 1 over x to the 2/3. If I try to evaluate that at 0 now, I'm going to get 1 over 0, which we know means we have either the limit, our limit is either infinity or negative infinity. So we can check the left and the right. So think about plugging in a number a little to the left of 0, like negative 0.1. If I take the cube root and then square it, I will end up with positive infinity. Same idea if I take the limit as x approaches 0 from the right, plug in a number a little bigger than 0, I will get positive infinity. So that means this limit is equal to positive infinity. And so that really tells us, though, this is f prime of 0 that we set up. F prime of 0 does not exist. Remember that when limits are infinity, the limit doesn't exist. So our limit doesn't exist, so our derivative doesn't exist, and really, because we showed this part here that either side was infinity, then what we can say is that f of x has a vertical tangent at x equals 0. Okay, so because when I set up my limit for my derivative, I got infinity, or in this case, from the left and the right, then I know that I have a vertical tangent there. And again, it's not enough to just say the derivative does not exist. I specifically would have to say the left or the right is infinity. Let's try another example. So we're going to think about f of x, which is x minus 2 squared plus 1. And we're going to try to find the derivative when x is equal to 2. So you may remember that this is the graph of a parabola. It's written in vertex form, so I can tell that my vertex is at 2, 1. And then just our normal parabola shape. Just making a sketch here, it's not perfect. And so I'm trying to find the derivative of f when x equals 2. And so again, I'm going to use my same type of formula. So I'm finding f prime of 2 here. That's the limit as x approaches 2 of f of x minus f of 2, which would be 2 minus 2 squared plus 1, or just 1 when you simplify that, all over x minus 2. And so in the numerator there, I have x minus 2 squared plus 1 minus 1. So I just have x minus 2 squared all over x minus 2. And so you might notice here my x minus 2's will cancel out 1 in the numerator and the denominator. And so then I'm just taking the limit as x approaches 2 of x minus 2, and I get 0. And that's an okay answer to have. What it tells me when my derivative is 0 is that I will have a horizontal tangent at x equals 2. So when I draw my tangent line, it will be a horizontal line. So horizontal line is, or horizontal tangent is synonymous with your derivative is equal to 0. Now let's think about the graph of absolute value of x minus 2 when x equals 2. So that's going to have our normal V shape for an absolute value function, but it's shifted right too. So it looks like this. See if you can estimate from the graph what the derivative is at 2. Okay, so let's go ahead and actually calculate the derivative now. F prime of 2 is going to be the limit as x approaches 2 of the absolute value of x minus 2 minus the absolute value of 2 minus 2 all over x minus 2, which just gives us the limit as x approaches 2 of the absolute value of x minus 2 over x minus 2. If I try to evaluate this right now, I'm just going to get 0 over 0, and there's nothing really I can do to factor or cancel. And so again, what we're going to do is split up from the left and the right. You might remember we did some limits like this in Unit 1. So if I plug in a number a little to the left of 2, such as 1.9, I would get something positive in the numerator, but negative in the denominator. So if I plug in 1.9, I would get positive 0.1 over negative 0.1, which would give me negative 1. And so that is actually going to be negative 1. You could also try to plug in positive 1 and see what you get. You'd still get negative 1. If I plug in a number to the right of 2, let's just say 3, I get positive 1 over positive 1, which is positive 1. Since those limits do not match, I can say that this limit does not exist. And so this is an example where just because the derivative doesn't exist doesn't mean I have a vertical tangent line. So there's actually a different reason why this limit doesn't exist here, and you could see it from our limits. This is like a left derivative and a right derivative. If I look at the slope of this line on the left, I can see that that slope is negative 1. If I look at the line on the right, I can see that that slope is positive 1. And so at 2, those slopes are not matching up. And since the slopes don't match on the left and the right, then my derivative doesn't exist, and I cannot actually draw a tangent line there. So when I have corners like that, I cannot draw tangent lines. So we just saw two cases where our derivative doesn't exist. One was at a vertical tangent, and another was at a corner. And so in calculus, we're interested in examining whether functions are differentiable. That means you can differentiate them, or that their derivative exists. So some definitions: a function is differentiable at a point if and only if f prime of c exists. So if the derivative exists at that point, then we call it differentiable. I can extend that to an entire interval. So a function is differentiable on an interval from a to b if and only if f prime of c exists for every value on that interval. And finally, a function is differentiable itself. Notice not on an interval or at a point, but just is differentiable if and only if the derivative exists for every value of x equals c in its domain. So very specifically, polynomials, sine, cosine, and exponential functions are differentiable functions, and they're differentiable for all real numbers because their domains are all real numbers. So those are important functions for us to keep in mind, that they are always differentiable. So a way to think about this graphically is that a function that is differentiable is smooth. So we talked about continuity, like a function is continuous if I could draw it without lifting up my pencil. The graphic way to think about differentiability is that it's smooth. So some ways that a function could fail to be differentiable. So if it has a corner, kind of like that absolute value function, if it has a cusp, so this is like the graph of x to the 2/3, I like to call it a bird graph, or if it has some mix of that, so it's like a straight line and then a curve or something like that. So some kind of sharp turn there, then it will not be differentiable. If it's not continuous at x equals a, then it is not differentiable at a. And so that could be a hole, it could be a jump, it could be a vertical asymptote. Automatically, if you're not continuous, you cannot be differentiable. The last one, number 3, is if a curve has a vertical tangent at a. So that's like the one we saw with the cube root. So if it has a vertical tangent, it is not differentiable. Let's take a look at some graphs and decide if they're continuous, differentiable, or neither at the selected value. So in example A, I can see I'm looking at x equals 3. So right here, I notice there's a jump there. That means that automatically my function is not continuous. And if my function is not continuous, it cannot be differentiable either. I'm going to abbreviate here. At B, I notice I have a removable discontinuity at x equals 1. So this is not continuous, which means it's also not differentiable. So I cannot draw a tangent line at that point. On C, I'm looking at x equals 0. It is continuous. I can see it's all connected, and it's differentiable. And to be sure, I could draw a tangent line there, and I notice it's horizontal. This is actually one of those examples of a horizontal tangent. At D, my function is continuous. I see it's connected. But notice it has this sharp turn here. And so I'm coming from one slope on the left and a totally different slope on the right. This is an example where it's not differentiable. So we would call that a cusp. See if you can do E through H on your own. So pause the video now and check back in a moment. Okay, for E, I see I have a vertical asymptote at x equals 2. So this is not continuous, which automatically makes it not differentiable. F, I have one of my absolute value type graphs. It is continuous. I don't see any holes or jumps or anything like that. However, because I have that corner at 0, it is not differentiable. On G, at x equals 2, my graph is continuous. I don't have any breaks or anything like that. However, I do have that sharp turn at 2, so this is not differentiable. And finally, H, I see that my graph is continuous. However, this is an example of that vertical tangent line. And automatically, when you see a vertical tangent line, you should know that it's not differentiable. So a couple things to keep in mind. If a function is differentiable, so it's smooth, then it must also be continuous. So if a function is differentiable, then it must be continuous. However, the converse of that statement doesn't have to be true. Just because a function is continuous, it is not necessarily differentiable, and so we saw some examples of that above. However, if a function is not continuous, then automatically it's not differentiable. So keep those things in mind. So we're going to practice finding the derivative numerically now. That means from a table of values. So in this problem, we know that this table gives us the body temperature in Fahrenheit over time of a polar bear on a very cold Arctic day. So it asks us to find t prime of 5.5. When we see that derivative, it's really asking me for the slope of the tangent line at t equals 5.5. So I don't know what this graph looks like exactly, so I can't draw a point at 5.5, but it does say to estimate. So pay attention to that word estimate, because that can give you a clue on how to do this problem. So essentially what we want to do is just approximate what the slope would be. And so what I'm going to do is choose 2 points that are around 5.5. So I'm going to use 5 and 6. And then I'm just going to use my normal slope formula, change in y over change in x. So t of 6 minus t of 5 over 6 minus 5. And now let's actually plug in those y values. 90.45 minus 90.73 over 6 minus 5. Now on the AP test you could actually leave your answer like that, except we are going to give some units since it was given in the problem. But since we're working it out together, let's go ahead and simplify. That would be negative 0.28. And then the units, my units of the numerator, the temperature was degrees Fahrenheit. My units in the denominator was over time, so degrees Fahrenheit per minute. That is my answer. So if you're asked to approximate a derivative from a table, it's just slope of 2 points around it. So next is a common AP style problem. We're given a graph of a function. Pay attention that this is the function f. Okay, so this is the graph of f. You always want to identify because sometimes they'll give you the graph of a derivative or some other function instead. It asks us to find f prime of 4. So what that means is find the slope of f at 4. So that could be the tangent line or the graph itself. Now pay close attention to this graph. You'll notice that the axes are ticked off every 2. So 4 is actually right here, and so I want to find the slope at this point. That means I want to find the slope of this segment. So since it's a whole line, I can find the slope of the whole line. And so I'm just going to use those points. 13 minus 1 over 6 minus 0. That gives me 12 over 6, which is 2. And so my derivative f prime of 4 is 2. So when I look at the graph of f, if I want to find the derivative, it is just the slope of the graph. In example 6, it tells us about a function f that's defined on the closed interval from -2 to 16. The graph of the derivative is shown here. So again, pay attention, this is the graph of the derivative. So it's talking about some other function f of x, which is not shown. The one that is shown is f prime. It tells us the point 14, -2 is on the graph y equals f of x. So that tells me f of 14 is equal to -2. Again, that's not this graph, it's some graph that's not shown. And it's asking me for an equation of the tangent line. So pay attention to what it's actually asking you for. To the graph of f at 14, -2. So remember that I need to have a point and a slope in order to find my equation of my tangent line. So the point was already given to me, 14, -2. To find the slope, I need to find the derivative at that x value. So I need to find f prime of 14. In order to find f prime of 14, I'm looking at the graph of f prime. And so what that means is I'm just going to find the y value at 14 because this is already the graph of the derivative. If it were asking me for the derivative of this graph, then I would think about slope. So I'm looking at this coordinate here, 14, 3. So that means my slope is 3. So the y value of f prime. So now I can write my tangent line equation. Y minus y1 equals my slope, my derivative, 3 times x minus 14. And you can leave your answer just like that. I guess we should check and make sure we see that the multiple choice option is there for B. Otherwise, you might have to manipulate it a little bit to make it match up. Last example, number 7. We know that the line 2x plus 3y equals k is tangent to the graph of y equals f of x at the point where x equals 5. And it's asking us for the value of the limit as x approaches 5 of f of x minus f of 5 over x minus 5. Hopefully you recognize that formula. That is asking us for f prime of 5. And what that means is f prime of 5 is asking me for the slope of the tangent line at x equals 5. Well, we don't have the slope of the tangent line, but we have the equation of the tangent line. And so in order to find the equation of the tangent line, I need to put this equation in slope-intercept form. So in other words, I need to solve for y. So I would have 3y equals negative 2x plus k, and then divide by 3, and I get y equals negative 2/3 x plus k over 3. I don't even need to know what k is because all I care about is the slope, which I know is negative 2/3. So that's the coefficient when I'm in y equals mx plus b form. So my answer here is b. So again, my derivative is just the slope of the tangent line. I just had to rewrite it so that I could easily see what the slope was.